monobactam. So a monobactam here, it has extensive SAR studies that eventually led to the development of our famous monobactam called as treonam. Okay, so the monobactam nucleus really it exhibits weak antibacterial activity. Thus, as with the penicillins, compared with the penicillins and cephalosporins, because it has lesser substitution. Molecular substitution around the central nucleus is essential to realize the potential of the antibacterial of monobactam. So side chain for the SAR of our drug should be parallel to our penicillin and cephalosporin. So further, it was studied, and then we already and the medicinal chemist arrived to the discovery of astreonam. So side chain substitution of the monobactam nucleus leads to compound exhibiting primarily gram-positive activity. It has also an activity against gram-negative, but primarily sa gram-positive siya, of course, kay beta-lactam example man siya. In other words, it can be broad spectrum type of antibacterial. So, as mentioned, it should be the same with the penicillin and cephalosporin. So, we will expect addition or incorporation of small polar groups, the small polar groups like our amino, hydroxyl, carboxylic, or sulfonic. It can be added to our beta-lactam ring directly, okay, so that it can enhance the activity. But there are different when they develop monobactam, there are divergence or different results in the addition or in the yung parang pagkumpuni nila sa structure. Matagal nila nabuo ang perfect structure, which is now the astreonam. Okay? So the most striking gain in antibacterial activity of our monobactam is the addition of amino-thiazolioxime side chain. So as you look for the structure of astreonam, in the case of carbonyl activated and phosphate activated compounds, that would be helpful in achieving broader spectrum of activity pa rin sa ating astreonam. So the activity against gram-positive, so it can be closely related to penicillin, as I have mentioned, which is the very nature of the acyl side chain, yung ating COOH side chain, in the beta-lactam ring. So, yun siya. And then, so, ano pa bang pwede natin idagdag sa monobactams? Ito na siya, si astreonam. So, this is how astreonam looks like. So, as you can recall, ito yung ating original structure for astreonam. And then, there are a lot of additionals here. It took a while to develop the structure of our astreonam. So, the SO3 here, you can see my cursor, the SO3 here, in the SO3 activated molecule for substitution, this is essential for beta-lactamase stability. So take note that the SO3 is for beta-lactamase stability. So another is incorporation of 4 substituents on our substitution here. Allows better activity, especially for, it is expected for gram-positive, but especially it has activity on gram-negative. Ang preference, according to studies, ang final structure ng astreonam has preferential activity on gram-negative rods. Okay. Now, ma'am, where is the third or yung ating na-mention kaninang carbapenems? Are examples of carbapenems? Di ba? Wala pa pala. Kasi I give this lecture before, commonly after infectious diseases na kasi. So, If you can recall, carbapenems, it has an ending, di ba? Penems. So we have the very famous imipenem and meropenem. So these are restricted antibacterials because they have a very broad action, spectrum of activity. Now, basing on how I dissected the beta-lactams, the penicillin, starting with penicillin, then followed by cephalosporin and aztreonam. In case you're wondering why it's not part of the lecture, I already included it in the activity. I will ask you, how will you identify the specific structure of imipenem and meropenem the basing on my lecture, because they have almost generally the same principle, the upgrades. Okay, so we have later on in our activity the imipenem and meropenem. So I hope you listen very well how I dissected a while ago penicillin, cephalosporin, and monobactam, the aztreonam. Okay, para ma-discuss nyo siya mamaya yung structure ng ating carbapenem. Okay?